Hello everyone, welcome to Math Q&A. In this video, we're going to be looking at an infinite geometric series. So I did mention in the previous videos that a geometric series is very interesting because sometimes it converges and sometimes it doesn't converge. Well, let me explain that in this video. Now, let's take, for example, let's look at a geometric series where we've got 2, 4, 6, 8, 10. Let's look at something like that. Let's say we've got 2, 4, 8, 16, blah blah blah, all the way up to infinity. And let's take an example of a geometric sequence. Let's look at 18, let's look at 6, let's look at 2, let's look at blah 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 up to infinity. Okay, I think that if you look at these terms of the sequence of the first series, as it goes up, you can see that they're increasing. And well, don't even think that this thing will actually stop increasing. As n goes to infinity, this thing keeps on getting bigger and bigger. Even at infinity, it still keeps on continuing. So you can see that when you sum all these values, actually the sequence itself doesn't converge. Let me tell you something. By convergence, we mean by when n becomes very big, this thing becomes very small. It converges, and by converging, it means that at some point it becomes very, very close to zero. Okay, so when you say something converges, that's what you mean. A value converges. As n goes to infinity, as n becomes very big, that means this values become very small. Okay, now let's look at the series. Now, the second one, you can see we've got 18, so 6 divided by 18 is 1 over 3. 2 divided by 6 is 1 over 3. You can see that our r is actually not like a value that is bigger than 1. Now, there's something interesting about that. Now, let's actually just continue. Here we've got 1 over 3. Here we've got 1 over 3. Just keep that in mind. Here we've got 2, and here we've got 2, and here we've got 2. Don't forget how we get these values. We divide the second term by the current term. Okay, it's very important. Now, let's continue. Now, our r here is 2. Our r here is 1 over 3. So already you can see what's happening. Well, but let's just look at this, like the sequence itself. You can see that the first value of the sequence is 18, second value is 6, third value is 2. Okay, now let's find the equation of this sequence. It's going to be Tn is going to be equal to a multiplied by Rn minus 1, where our a is 18 multiplied by r, which our r is 1 over 3 multiplied by n minus 1. Let's take our calculator and find what is the value of n 10, for instance. So we're going to have 18 multiplied by 1 over 3 exponent 10 minus 1, and the value is 0.00091. We can see that as these values become very big, this thing actually gets very, very small. And when I put 50 there, it becomes drastically small. If I can put 100, this thing becomes more and more smaller, until if I go to 1,000, this thing looks like it goes to 0. It means that the second sequence converges. By converging again, it means that as this thing increases, it goes to 0. So think about this. Are you aware that now, when you sum these values all the way going to infinity, even before n reaches infinity, this thing goes to 0. It means these values actually become very small. So that's like whenever you add a value to a specific number, it's not even sin. Let's say, for instance, if you add a 1 plus 0.000000000000000000000. Let's keep on going, and I put a 1. So 0001, we add them, your calculator will say this thing is a 1 because those numbers are negligible. It means that adding 0.0000000 at 1,000 zeros to 1 is the same as 1 because all that is negligible. So that's the very same thing we have here. We've got 18, we've got 6, we've got 2. As these values go down, they become very, very small to a point that when you add them with the first values of this thing, it's not important and it doesn't change what the value is. That's what we mean by convergence. So at this point, we actually are going to be talking about this difference. Well, in the previous video, we talked about finite geometric sequence, meaning we had a formula for calculating what the sum of a geometric series. If you actually want to limit, let's say you want to say I want to find the sum up to a specific number, but then we have another equation which we use if you want to find the value of the series when we actually are considering the whole series up to infinity, and that equation is With the two examples that we discussed above, we're going to look at the equation of an infinite geometric sequence, which again is Sn is equal to a over 1 minus r. Now here our r is from -1 up to 1. We mean that we only want to find the geometric series of equations that converge. This equation only applies to converging series. And by converging, like I said, it means that the values become small, Sn becomes big. Okay, so the sequence that I showed you guys previously is actually 18, 6, 2 going all the way down, and our r there was 1 over 3. So let's find our Sn for that. Is that equal to a? Now a is actually 18 in that instance over 1 minus r, which is 1 over 3. So the sum of this thing up to infinity, meaning if we decide to sum those values, they will end up giving us 27. Okay, let's try this rather. Let's try this. Okay, so now let's actually make a sum. Let's make a sum of this thing. Okay, now I'm going to try to make a sum with my calculator and show you something really interesting. Now from there, I'm going to say, okay, fine. Well, I'm going to sum the values of that series. Okay, now Tn is equal to a multiplied by r and minus 1, where a is 18, multiplied by 1 over 3 and minus 1. Now I'm going to represent this thing like this, and is equal to 1 up to some value which I'm going to be incrementing, going up, and then 18 multiplied by 1 over 3 and minus 1. I'm going to put this thing in my calculator and say that the sum of this series, which is our geometric sequence, as we go to infinity, what happens? Does it really converge to 27? We can prove that. Okay, now let's do that. We're going to have a series from 1 up till 2, which is 18 multiplied by 1 over 3. Okay, don't forget the calculator, this calculator, it doesn't have n, so we put x rather, minus 1. So if we do that, if we go from the second to the third one, we find that the answer of the sum is actually 24. That's interesting. We find 24. Now if we go to 3, we find 26. Okay, and that is because the equation is 18, 6, 2. Okay, now if you're going to find a value after 2, it's actually 2 multiplied by 1 over 3, which is actually 2 over 3, all the way to infinity. Okay, let's keep on summing. Let's go then keep on summing. Let's say up to 3, from 1 up to 3, we've got 18 multiplied by 1 over 3, exponent x minus 1. We get 26. And then let's go further. Now let's see 4. Now we get 26.66. Okay, interesting. Now let's go 5. We get 26.88. What's going on? Seems like this thing is converging. If we say 10, this thing is now 26.99. This thing doesn't want to go beyond 27. We can see what's happening here. If I say 20, let's just give it time, because it probably might take some time. We are summing all the values of this geometric series from 1 up till 20. And you can see that the answer is 26.9999999. So this shows us that the sum of this geometric series as n goes to infinity approaches 27. Meaning when we sum all the values of the arithmetic series, don't forget here I want to sum 20 of them, but if you go further, if you go to infinity, meaning if you just go all the way up, this will eventually just be 27. Okay, and that is the end of the video. Okay, thank you.